Richard Feynman once wrote that nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry. The more scientists study the physical world, the more they realize how true this was. For centuries, we studied physics by dividing it into disciplines. Newton gave us mechanics, Fourier develops the mathematics of heat transfer, Navier and Stokes describes fluid motion, Maxwell unified electricity and magnetism. One equation at a time, humanity learned the rules governing the physical world. But there was a problem. Reality never agreed to stay inside these categories. A battery is not only electrochemistry, it generates heat, and that heat affects its performance. An aircraft wing is not only a structural problem. Airflow deforms the structure, and the deformation changes the airflow. Even the human body combines fluid, heat transfer, electrical signaling, chemical reactions, and biomechanics, and more. It almost can never be understood from one point of view. What we often call a single physics problem is usually a simplification of a more complex reality. And that realization eventually led to one of the most important ideas in modern engineering, multiphysics simulation. I wanted to show you what multiphysics actually means. When people hear the word multiphysics, it often sounds like a marketing term. In reality, it is simply the process of solving multiple physical models together. Consider the human voice, for example. Every time we speak, air is expelled from the lungs and passes through the vocal folds inside the larynx. As the airflow accelerates through the narrow glottal gap, that is the gap between the vocal folds, pressure forces develop on the tissue surfaces. These forces cause the vocal folds to form. Then, the deformation immediately changes the shape of the airway, which alters the airflow itself. The new airflow produces different pressure distribution, creating new deformation of the vocals, and that repeats over and over, creating the vibrations. In other words, the airflow affects the vocal folds affects the airflow, and this is called self-oscillation. I bet most people think that the vocal folds actually have muscles that vibrate continuously, but this is not the case. It's more interesting than that. This continuous feedback loop is called a fluid structure interaction. Here's a simulation from a research that I have conducted 2 years ago. At first glance, speaking appears simple, so we do it every day without thinking about it. Yet from an engineering perspective, voice production involves fluid dynamics, structural mechanics at least, and then acoustics and tissue biomechanics, and in some cases even heat and mass transport. Obviously, you could not simulate this phenomena with only one physics. Mathematically, however, it is extremely difficult because it requires coupling different sets of equations. For example, in this case, on one side we have fluid dynamics, that is trying to solve for the field of velocity inside our domain. On the other side, we have the structural mechanics, that is trying to solve for the displacement field with this equation. The real challenge is the mathematical handshake between them. We have the two different domains. The force exerted on the fluid must equal the force experienced by the solids at the interface. So we use this equation. Here is the force on the fluid, and here is the calculated field of velocity in fluid. This equation allows the two completely different branches of physics to communicate with each other. Engineers did not just couple fluid and structure, they also started coupling heat transfer, electromagnetism, acoustics, chemistry, mass transport, and many other phenomena together. The aim was no longer to solve equations individually, but rather to solve reality. This shift became possible because of another revolution, computational engineering. By the middle of the 20th century, engineers increasingly faced problems that could not be solved analytically. For example, aircraft, power plants, semiconductors, and biomedical systems that were simply too complex. Then came the finite element method. By the 1956, Ray Cloft introduced the term of the finite element method, one of the most influential developments in engineering history. The finite element method transformed engineering, and it laid the foundation of many simulation softwares, including COMSOL Multiphysics. In 1986, Svante Littmark and Farhad Saidi found COMSOL in Stockholm, Sweden. Initially, the company focused on numerical modeling tools based on partial differential equations and finite element analysis. During the following years, the software evolved through a MATLAB-based environment that gave researchers direct access to the mathematics behind their simulation. In 1998, COMSOL released FEMLAB, and in 2001 launched a 3D FEMLAB that first addressed the multiphysics ability. Earlier versions functioned largely as MATLAB toolboxes, but FEMLAB 3.0 took a major step toward becoming a standalone simulation platform. While it maintained compatibility with MATLAB through its file structure and scripting capabilities, users were no longer required to own MATLAB to use the software. As the computing power increased and engineering systems became more interconnected, this approach became increasingly valuable. In 2005, FEMLAB was officially renamed COMSOL Multiphysics. The new name reflected a larger vision. The company was no longer emphasizing finite elements alone, it was emphasizing the coupling of physics. As the years progressed, COMSOL expanded into structural mechanics, fluid dynamics, heat transfer, acoustics, electromagnetism, batteries, fuel cells, plasma physics, microfluidics, and many other disciplines and systems. In 2014, COMSOL Multiphysics 5.0 released, including the application builder. In 2018, COMSOL Compiler was released. In 2021, COMSOL Multiphysics 6.0 released, including the model manager. Today, researchers use COMSOL to study diversified fields. One of the fascinating things about COMSOL is that researchers from completely different disciplines often end up using the same mathematical tools and the same software. If you use COMSOL in your research, tell us what fields you're working on and what are you simulating. Or if you're a beginner, tell us what are the challenges you're facing. Let's communicate. As I searched through the literature, I found that the number of scientific publications involving COMSOL has grown dramatically over the last decade. If you search databases such as PubMed, you can see this growth yourself. This increase reflects something larger than the success of a software package. It reflects the rise of simulation-driven science. Simulation is no longer just a tool for verification. It has become a tool for discovery. Perhaps that is the most interesting lesson from the history of COMSOL. The story is not really about the software, it's about how engineers and scientists learn to reconnect the equations of physics. For centuries, humanity discovered those equations one at a time. Mechanics, heat transfer, fluid dynamics, electromagnetism. Today, we finally possess enough computational power to combine them and study systems in their full complexity. The history of COMSOL is therefore part of a much larger story. It is the story of the humanity's attempt to simulate reality itself.